Soumya, Danya, all yours. Thank you.
Thanks, Pep. Hi, I'm Soumya and I'm from NVIDIA.
Hi everyone, this is Dhanya and I'm an engineer with NVIDIA too.
And in this session, we'd like to talk about how we are implementing custom CPU pinning and integrating it with KubeVirt. So firstly, what is CPU pinning and what are really the benefits that you see? So if you launch a KubeVirt VM, the Virt launcher pod as well as the KVM VM that's running inside the pod are both floating across all the CPUs that are available on the underlying physical node. So let's say my node has 16 logical cores or CPUs. That means my Virt launcher pod as well as the VM are going to be floating across CPU sets 0 to 15. This means at any point of time, the workload that's running in the VM could be switched to a different CPU core. So it's not bound to a specific CPU on the node. Many workloads are not really sensitive to this type of switching and not being bound to a specific core, but there are a lot of workloads like HPC workloads, for instance, that are sensitive to this. They're very sensitive to context switches or sensitive to cross-socket memory traffic, and they may also have requirements for optimizing performance, like allocate having both hyperthreads from the same physical core allocated to them. So the main purpose of CPU pinning is to boost performance, wherein you pin the vCPUs in the VM to specific CPUs on the underlying node. That way, they are always bound to the CPU and they're not, switching to different cores through the life cycle of the VM. KubeVirt does actually support pinning as long as you're using CPU Manager framework. But CPU Manager framework is the be all and end all of pinning. There are certain gaps that are not addressed, at least in the current version of it. Firstly, it just supports two policies. One is a static policy and one is a none policy. None is basically a no-op. So effectively, you have just one policy and it's not easily extensible. So let's say I want to implement pinning based on my specific hardware and my specific hardware requirements. It's not just plug and play. I can't just add a new policy and integrate it. So the framework is pretty, it's with kubelet. So if you want to introduce any custom changes, then you maintain your own fork of kubelet, and that's not easy to do. Secondly, one of the requirements for CPU pinning with CPU Manager is that your pod should always be of guaranteed QoS class. What that means is your requests, CPU requests, must strictly match with your CPU limits, and you should always request only whole number of CPUs. This means I can never use pinning for, say, pods that are of best effort QoS class or burstable QoS class. But this is probably the most problematic or the biggest gap in my opinion. The way CPU Manager functions is that of all the CPUs that are available on a node, there's some reserved for kubelet and there's some reserved for system processes and things like that. So if I have a node with 16 CPUs, 100 millicore could be reserved for kubelet, could make other reservations. So the rest of the CPU, which might be something like 5900 millicore, would be put in a shared pool. So if you have an incoming request that is requesting for, that's of QoS, guaranteed QoS class, and that's requesting for pinning, then those CPU sets are removed from the shared pool and put in an exclusive pool. And that pod is guaranteed these exclusive CPUs for the entire lifetime of that pod. And there's no other system process or no other pod that can run on these CPUs. So any pod that doesn't have this exclusive CPU request would be running from the shared pool. So this means it's theoretically never possible for me to, bind all the underlying CPUs that are available on my node to my VMs. So if I have 16 CPUs, I can never create VMs that are able to use all the 16 CPUs because of the shared pool and because of kubelet reservation and things like that. So I'm not able to densely pack VMs with CPU Manager as I can without it. So that's the biggest bottleneck that we were experiencing. Um, and it's also best effort based. So it's going to always try to allocate from the same socket, from the same NUMA, as much as possible. But if it can't, it's just going to do a best effort allocation, and that's going to lead to fragmentation. So that's where we started experimenting with custom pinning, and really our requirements were, being able to pin all the available CPUs on the node to the guest VMs. So that means allowing all the other pods, kubelet, system processes, CRI to float across all the CPUs on the node. So the guest can be pinned to exclusive specific CPUs on the node, but other processes can float across all the CPUs. And one requirement that we have is that we don't really need exclusive access to the CPUs that they are bound to. So if my VM is say pinned to CPU 0 and 1, it would continue to remain pinned to these CPUs for the lifetime of the VM, but that does not stop other processes from stealing time from CPU 0 and 1. So that's that's what we are trying to achieve. And secondly, we want to be able to support a lot of policies. If I have a new hardware and I want to have a very specific optimization for it, then I can implement it as my own custom pinning policy. Thirdly, I want to be able to set vCPU pins in my VM. That means I want to pin my vCPUs in the VM to specific pCPUs on the node, as well as pin all the threads that are associated with the VM. So that would be like KVM threads, IO threads, worker threads, so on and so forth. And yeah, I also want to be able to do pinning with any QoS class. So if I'm going to spin up a word launcher pod of best effort class, I want to be able to use pinning in that pod and not just for guaranteed QoS class. So how are we going about implementing this? So it was actually pretty straightforward. Kubernetes has a device plugin framework. In fact, KubeVirt uses device plugin framework too. And this allows you to, advertise your resources as extended resources on the node. The main advantages of using device plugin framework is that it integrates very well with topology manager and also other device plugins. So if you want to allocate devices based on affinity or want to be able to support different topology manager policies, then it's very easy to do so. So device plugin basically runs as a daemon set on every node in the cluster, and it's going to discover the underlying CPU topology of the node, and it's going to advertise the available physical cores on the node as extended resources. So one of the nice things about the device plugin framework is starting with Kubernetes version 1.19 and upwards, it has this preferred allocation method that's supported. This means you can use this preferred allocation method to implement your own custom algorithm for allocation. Without this, the devices would just be allocated at random without any algorithm deciding which device should be allocated. But because of this preferred allocation, I can, create a number of allocation policies and implement a unique algorithm of which device needs to be picked based on that policy. And so this device plugin is mutually exclusive from CPU Manager. So we don't managing pinning on the same node. So this device plugin will not run on a node where CPU Manager is running. And the best part is it's very easy to integrate with KubeVirt. KubeVirt's already integrated with things like GPU device plugin, SRIV device plugin, and it's very straightforward to hook it up with KubeVirt. I think now Danya will walk over how the API looks like and things like that.
Yeah, thanks, Samya. So, in order for custom CPU pinning to work, there are some dependencies and assumptions. So, one of them is that the Kubernetes version should be 1.19 or higher, which is required for the preferred allocation, like Samya just spoke about. So, without this, you can't implement your own custom policies and so on. And the next requirement is that the KubeVirt version should be 0.24 or greater, and hyper-threading should be enabled on the node. So this is done by default, but there is a check to ensure that it's always in place. CPU manager should be disabled, or the policy should be set to none, which is essentially a no-op. This is because CPU manager and this custom CPU binning are mutually exclusive, and we can't use both of them at the same time. So there were some changes that were needed to be made on the KubeVirt side to support this custom CPU pinning. One of them is that there is the new feature gate called custom CPU placement, which needs to be enabled on the KubeVirt side. And then in the VMI spec that the user requests, there is a Boolean value called custom CPU placement, which needs to be set to true in order to support requesting for CPUs. And then there is also an option to specify the cache level or mode in the VMI spec. And this entire thing can be abstracted using VMI presets, as we see on the next slide. Next slide, please. Yeah, so in this, this is an example preset where you can see that under the spec domain, the custom CPU placement boolean is set to true, and then the cache mode is set to pass through, and there are a number of cores and threads and sockets being requested. Next slide. Okay, so there's also an admission webhook on the Virt API side in KubeVirt, which validates the incoming VMI for correctness. So it rejects the certain VMI requests that don't follow certain rules. Like suppose the CPU manager feature gate is enabled, then it rejects the request because CPU manager and custom CPU pinning cannot be used at the same time. And then if the custom CPU placement feature gate is not enabled, or the dedicated CPU placement value is set to true, or and it also checks if the number of cores and threads in the request is even. So it should be even in order to prevent fragmentation of hyperthreads. So it rejects the request if it's odd, and if the number of cores and sockets and threads are not explicitly specified, it's assumed to be 1. And the admission webhook also validates that the user is not requesting CPUs under resources, requests, or limits, and is only requesting them under the spec domain CPU part of the spec. Yeah. Regarding when to use what, so like Samya mentioned, there's a concept of shared pool with the CPU manager, which means that you can't use all CPUs because of the shared pool, and since there is a requirement of pinning all CPUs to the guest VM, and the guest VM will be pinned to specific CPUs, and then other processes can float across all of the CPUs, and there's no need for exclusive access to CPUs with the custom CPU placement. So in such use cases, we'll make use of the custom CPU placement and not the CPU manager. Yeah, I think now Samuel will go with the flow and then do a quick demo.
Thanks, Tanya. So this is the control flow of what happens when there's a VMI request with custom CPU placement set to true. So the request first hits the API server, and then it goes to the Virt API, which is going to validate the request and choose whether to admit it or reject it. So if it passed all the checks that we were talking about earlier, the request is admitted, and Virt controller then will translate the VMI spec into a pod spec. So what it's essentially doing is it's converting the Boolean that you set in the VMI spec custom CPU placement true into the corresponding extended resources that are exposed by the device plugin. And that would be added as requests and limits to your word launcher pod spec. Once that's done, the scheduler picks a node where this word launcher pod could run, and it's scheduled. And kubelet on that node then talks to the device plugin using the device manager framework, and it's requesting for allocation of these extended resources. So inside the the CPU device plugin is basically running one or more allocation policies, and depending on what allocation request was made, it's going to send an allocate response with the appropriate CPUs returned. And kubelet then sets these CPUs as an environment variable on the compute container in the word launcher pod. So once the word launcher pod starts to run, you can query these environment variables and set it as part of, and you can even run some validations to make sure that you got the appropriate number of CPUs. And you can, if you have some special requirements, say they have to be thread siblings or they're from the same core, things like that, you can add whatever checks you need to validate that the response that was returned by the device plugin was indeed right and matches your request. Once you do so, you can set these CPUs as the vCPU pin in your CPU tune element in the DOM XML. Once you do so, then you can start running the domain, and when your VM comes up, it would have the pin set on each of the vCPUs. So I'll show you a quick demo so that this is all a bit clearer, and I've just talked about this in detail in the next slide, but I think a demo would make a lot of sense. Are you able to see my terminal?
I can't see it yet somewhere.
Okay. I think I have to go back and change the sharing settings. Sorry. Share screen. Application window. How about now?
Yes, we can see it now.
Okay, so firstly, let me show you what's running in my cluster. So I have 3 nodes, and I have deployed my CPU device plugin as a daemon set, so it's running on all 3 nodes. So if I do a describe node and query what are the allocatable resources and allocated resources, this is the resource that is exposed by my device plugin. So it's called nvidia.com course and socket. And an interesting thing to note is the first 2 nodes are single socket systems. So the device plugin is exposing just one extended resource, but my third node is a dual socket system. So it's exposing 2 device resources. So it's running 2 device plugins for each of the sockets. So it's exposing it this way. So let me first show you an example of what preset I'm using and what VMI I'm trying to launch. So I've created this preset that's requesting for 8 vCPUs in all, split as from 4 cores and 2 threads. And I've set my custom CPU placement to be true, and just memories and other devices that I need, and I've set a label. And now I have a VMI that's just going to call on this preset. So it's just using this preset that I showed earlier, but otherwise it's a pretty simple VMI spec, just using a default bridge interface and a PVC and a cloud init volume. So I'm going to launch a VM. So like I said, it's using this preset. I'm creating the persistent volume, and then I'm spinning up the VMI, just waiting for the VM to get to running state. And then we're going to see a bunch, query a bunch of things on the word launcher pod as well as the VM. The VM's got into running state. So this is my VM. It's running on one of my nodes that has a single socket system because I requested for single socket. And if I describe my word launcher pod, you can see that in the limits, requests and limits, this extended resource has been requested for. So I'm asking my VM preset wants 8 vCPUs in total, but I'm requesting only for 4 cores because I'm requesting for both the hyperthreads to be allocated from the same core. So there are 2 hyperthreads per core. So, 4 cores actually translates to 8 logical cores. So this is the physical core. If you look at the request, it's very interesting that the CPU request is just 100 millicores. This is the default CPU request. If I were to be using dedicated CPU placement, this would look like, 8 limits and request would be CPU 8 because it's going to request for exclusive access for 8 CPUs on the node. So this is one important thing to note. Instead of setting it as CPUs, we are just setting it as a different resource, which is what is exposed by my device plugin. And if I query my word launcher pod, this is the environment variable that has been set by my device plugin. So it's returning 8 CPUs in a very specific order. The order is that, CPU, the allocation is always in thread sibling pairs. So 0 and 8 are thread siblings, 1 and 9 are thread siblings, 2 and 10 are thread siblings, 3 and 11 are thread siblings. So this can vary upon depending upon your use case and whatever policy you require. But for me, I want my physical cores to be adjacent, and I want hyperthreads from the same physical core to be allocated together. So this is the desired allocation that I need, and that's what's being set as an environment variable by the device plugin. So if I query the CPU set running associated with my word launcher pod, you would see that it's actually floating across all the CPUs on the node. So my node has 16 CPUs, so it's floating from 0 to 15. I dump the DOM XML of the domain VM. You can see that there's been a CPU tune element that's been added, and this is what sets the pinning. So it's setting pin on vCPU 0 to be on pCPU 0, vCPU 1 on pCPU 8, and so on. So this order of pinning is what was dictated by the output from the device plugin. You can also see that I'm setting a CPU set over here. What this means is all the threads, like the KVM thread, IO thread, worker thread associated with the VM are all bound to these CPUs. It can float across these CPUs. They're not bound to specific CPUs. It can float across these CPU sets, but they can't run on any other CPUs on the host. And I'm also, implicitly setting modes to host pass-through and adding cache level implicitly. So if I now go and query the VM, you can see that the VM has 8 cores and 8 CPUs, and you can see that they are from 4 cores. So the order, you can see that they're from 4 cores. And on the node, if I query the allocated status and the allocatable status, you can see that it's allocated for of the extended resource for this particular VM. And the best part is how do I validate, that the pinning actually took effect. So for that, I'm going to just grep the KVM process on the node and see what are the allowed CPU list. So if you see over here, you can see that these are the vCPUs of the VM, and they have been pinned to very specific pCPUs on the node. Again, this is the order that was provided by the device plugin and the order we set in the DOM XML. And you can see that all the other threads associated with this process are floating across these CPU sets. Again, this is what we set as this element over here. So that's how we achieve custom CPU pinning for our use case. Let's stop sharing now. Does anybody have any questions or?
I think there's a question on the chat.
Oh, okay. Do you support VM migration or? Okay. So we haven't played around too much with VM migration, to be honest, because we've just been using bridge network. So that doesn't support migration, but I guess it's possible to do. I'm not entirely sure because we haven't experimented with it. But it should be possible to do because you can control the pin because it's just another resource that is exposed on the node, right? So when you migrate, you would pick a node that satisfies the requirements. So should be possible to do, I think. Could you comment on what are the main use cases for CPU pinning without isolation? So essentially, in my use cases, I have a set of nodes on which there are going to be very lightweight pods or processes, if any, running. And my main use case is to pack those nodes with VMs that can run my sensitive workloads. So I'm not going to have like elaborate daemon sets or anything running on those nodes. And my exclusive purpose for those nodes is to, run these very highly sensitive VM workloads. So since I don't have too many other containers to care about, I don't really it's okay if there are other processes or system daemons that are stealing some CPU time because again, everything is CFS quota because of how CPU limits work with kubelet, right? So at best, it's going to be throttled and I can control that by setting appropriate QoS class for the other pods that are running on my node. I mainly care about optimizing all the available CPUs on the node and being able to bind them to my VMs, guest VMs. So that's my main use case, to be able to use to be able to achieve pinning as well as use as much CPUs available on the node as possible.
Okay, so that's just made it on time for the end of the session. So thank you very, very much, Sonia and Tanya, for this